right, so we're going to do just a little bit of review for Chapter 5, which was all about sequences. And again, this is review from work that we've done earlier this year, so I'm not going to go into a ton of detail about each of these, but hopefully these videos kind of get you going back in the right direction because it has been a little while since we've done these. The idea with sequences is that we have a sequence of values that are following some set of rules. And kind of the biggest difference between sequences and just regular functions is that if we look at this one, for example, if it goes from 4 to 7 to 10 to 13, there's no value between 4 and 7. If you were talking about a normal number line, you could still say, well, there's values in between 4 and 7, but because we're talking about a sequence, this follows a very specific set of rules, and so we go from this to this without any values being in between. Okay, so the two I have up here, one of them is adding by 3. So one of the things we're trying to do is find out how the sequence is working or what rule the sequence is following. And in this case, our first value is 4, and it is growing by 3. Okay. In the second situation, our first value is 2, and it is multiplying by 5. If the sequence is changing by addition or subtraction, that is an arithmetic sequence. And if it's changing by multiplication, that is geometric. The other reminder I want to make is even if these are getting smaller and it looks like it's changing by division, it is changing by division, but we always want to try to keep in mind that it's also multiplying by a decimal or by a fraction. Try to keep in mind that a geometric sequence is always multiplying, even if it's getting smaller. The next thing we want to talk about is how we write an equation to represent a sequence. So a few reminders is that we replace y with the term t of n. This is still my output. Okay, it's just being represented in a different notation. And then we really write it the same as we would y equals mx plus b. Okay, so my slope or my rate of change is plus 3. So I'm going to write 3n. That n is now representing my input. So again, this is my output. This used to be a y, and this used to be an x, and now it's t of n and n. And then this was the tricky part, that even though this is the first number in the sequence, we still have to go back and find the 0th term. Okay, just for the sake of writing our equation. So if it's adding by 3 every time, I'm going to subtract 3, which is going to give me 1. And this is an equation to represent this sequence. Okay, now geometric, really working the same way. Okay, but because it's changing by multiplication, okay, we're going to write this as an exponential equation. Right, so once again, our multiplier is 5, okay? So we know that whatever number is next in the sequence is going to multiply by 5, okay? And then to find that start value, we would have to go back to the 0 term. So if it's multiplying by 5, I'm going to divide by 5, so it's going to be 2/5. My geometric sequence here is, okay, t of n equals 2/5 times 5 to the nth power. Again, this is just similar to y equals mx plus b, and this one is similar to y equals a times b to the power of x, and just using different notation. All right, now one more thing I want to talk about real quick is we also learned about recursive equations, which are equations that you must know the value before in order to find the next value. And these are explicit. These are called explicit equations. So in order to write a recursive equation, number one, you need to remember you have to write 2 equations. Okay, so to write a recursive, we almost always are going to start writing it the exact same way. This is telling us we're reading a recursive equation. And then right here, I am just going to write what is happening in the equation. So in this particular case, this is telling me that to find the next number in the sequence, take the number right before it and add 3. But in order to do this, I have to give a starting point or some value along in the sequence. Otherwise, this doesn't make any sense because I might know that I'm adding 3, but I don't know to what number I'm adding 3 to. So then your second equation would say something like this. So what this says is that the first number in the sequence is a 4. And just a reminder that I could put any number I wanted here. If I wanted to put a t of 3, I would just need to make sure that I put a 10 there because the third number in the sequence is 10. Okay, so this gives us kind of a reference point, and then from here on, we know that we're adding 3, okay? Or subtracting 3 if you're going backwards. All right, we're going to do the same thing here. So we're going to go t of n plus 1 equals t of n. And then I know that it is multiplying by 5. I'm going to write t of 1, and I'm just going to write what the first number in the sequence is. There we go. So these are recursive, and these are explicit. Not sure if you can hear my daughter downstairs, but I hope you're enjoying that as well. All right, there we go. This is sequences, both explicit and recursive. Hopefully that's helping a little bit as you guys are working through this week's assignment. Before we're finished today, I want to talk a little bit about laws of exponents. Again, review from earlier this year, but hopefully this will kind of get you going in the right direction. So essentially, we find 3 different things that are happening with exponents. And we are also assuming that the bases are the same in all of these circumstances. So if I have the same base, but they are multiplying, and I have 2 different exponents, the rule is that I can add those exponents together. So if I have x to the 3rd times x to the 5th, I can add the 3 and the 5, and it gives me x to the 8th. Remember when we used to do the expanded form, and we'd write just 3x's times 5x's and just counted those all up, and it gave us 8x's? That's what we're doing here. All right. Now, if you have a power to a power, make sure you notice the difference here. I have x to the power of a, and then that whole thing is to the power of b. That is different than this. And when that's happening, we can just multiply those 2 together. Okay. So if I have x to the 4th to the power of 2, I would multiply 4 times 2 and it would give me 8. Okay? And then lastly, if I have 2 bases that are dividing, I can subtract the bottom exponent from the top. So in this case, it would be a minus b. So if I have x to the 5th over x squared, I can subtract the 2 from the 5, which would give me x to the 3rd. Last thing that I think should wrap up this week's work, hopefully, is if I have a negative exponent, we can write the inverse of that by taking the negative away and putting everything underneath 1. Okay? The same thing could be true if we have something like this. We can write it like that as well. Okay? Now, another thing that oftentimes gets forgotten, it sometimes is not the most intuitive, is that anytime you have a power of 0, that is always going to be equal to 1. Okay? It doesn't matter what the base is. If the power is 0, the value of that is always going to be 1. So if I have 100 to the 0 power, that's still 1. Okay, so just keep that in mind as you're working through this week. Hopefully this is helpful. If you have any questions, please email me, send me a message on Instagram, call me, do whatever you need. But let's get through this week. All right, see ya.